In this presentation, we'll talk about how HyperLynx can help you reduce risk by verifying serial link designs for standards compliance before sending them out for fabrication. Let's start with the question, what do you do once PCB layout is complete before you send your board out to prototype fab? What do you do to verify it and know that it's okay to manufacture? Well, if you're like most people, you do one of three things. You design the board to vendor guidelines and then use visual design inspections to look for possible errors. And then you fab out the board and hope for the best. Or you get an external consultant to verify it for you. That means any change to the design requires another round of simulation, which costs more money. Or if you have access to an in-house SI expert team, you wait in line for their time, because they're typically already busy with someone else's project. Not surprisingly, we don't think of any of these are particularly great options. In this presentation, we'll review a better way to ensure your designs are ready for fab out. In our methodology, we start by running electrical design rule checks during layout to look for common problems. And then we're going to use standards compliance analysis to look at the system level interconnect and make sure it meets protocol requirements. And finally, once we've gotten as many problems off the table as possible, we'll use IBIS-AMI or vendor-based model simulation to predict how the system will perform with actual devices and settings. We call this methodology progressive verification, and it allows us to find layout problems as early in the design cycle as possible, with as little effort as possible. We deliberately separate verification into different stages so that we can defer time-consuming and expertise-intensive analysis, allowing us to make the best use of scarce SI experts. We start with simple analysis and then add accuracy in controlled stages, because the time needed to model and analyze the system increases as we make the analysis more accurate. That's true with any tool, not just HyperLynx. The time and expertise needed to perform simulation increases dramatically as analysis accuracy goes up. The board that we're going to be using for this demonstration is a dual-socket server motherboard based on the reference design for Intel's new 4th generation Xeon processor. This design has 16 DDR5 memory channels supporting a total of 32 DIMM slots. It has 10 PCI Express 5.0 channels operating at 32 gigatransfers per second for a grand total of 336 serial channels. We're going to look at simulation results for all of these 336 serial channels. The stack-up for our design was created in ZPlanner, which you can see on the other side of the wall behind me in the booth. We also added our own backdrilling information and added a few example layout problems so our analysis has something defined. So with that in mind, let's take a look at electrical design rule checks. Electrical design rule checks give us a fast way to find things that would require a lot of time and effort to find with simulation. This is in line with our goal of finding as many problems as quickly and easily as possible. In this case, we were able to check all 336 serial links for planes crossing in just under 3 seconds. We found 2 potential issues for consideration. Electrical design rule checks can tell us whether certain anomalies are present in the database and how to set things up for simulation. In this case, we checked all 336 serial links for backdrill info in 90 seconds, letting us know how to correctly set up our simulations. Whenever we find a potential problem using design rule checks, there are 3 possible outcomes. First, we might look at the issue and realize there is a problem that needs to be fixed. No further analysis is required. We simply need to go to the layout and fix it. Second, we might look at the issue and realize that no problem exists. The design is okay. And in that case, we mark the issue as verified and we move on. And third, it might not be obvious whether it's a real problem or not. And that's where we would use additional modeling and simulation to investigate. In this case, we modeled the part of the serial link that crosses over the split in the reference plane. And as we can see here, we modeled just that part of the net by itself to isolate the effect of the plane split. We actually modeled the net with and without the plane split so we could compare behavior, as we see here. You can see that while it's clearly a bad idea to have a serial link run over a split in a reference plane, the effect on signal behavior is actually quite small. And that's just for this small section of the net. The effect this would have at the full net level would be much smaller. So while we would probably update the layout to correct this issue, it isn't having much effect on our system margin at all. Once design rule checks have been run, we move on to compliance analysis, which focuses on system-level interconnect. How does compliance analysis compare to IBIS-AMI simulation, and why is it useful? Compliance analysis focuses on the channel itself, without vendor-specific IP. That means that compliance analysis can always be run, even when no IBIS-AMI models are available. The analysis ensures the channel meets the requirements laid out in the corresponding protocol spec. HyperLynx compliance analysis produces a detailed report of which channels passed, which channels failed, and by how much, so you'll know exactly where to focus your efforts. HyperLynx supports protocol-specific analysis for 210 different protocols and variants, providing the broadest standards-based support in the industry. It also has the ability to support a custom protocol. For our first analysis, we're going to analyze all 336 channels using 2D view models. Now, most of us would ask, why would anyone ever do that? We all know we should be using 3D view models at these speeds. There are two reasons why we do this. First, because it's fast. We can get results for all 336 channels in a few hours using a single computer. So as long as we take the reduced accuracy into account when looking at the data, we can derive useful engineering insights. Second, because if issues exist with 2D view models, they will certainly exist with 3D view models. By finding them quickly, it allows us to take problems off the table earlier. And finally, because this is a good way to ensure the database is set up correctly for a longer, more accurate run. This helps us save time and computational resources. One of the interesting challenges with a design like this is just trying to make sense of all the data a simulation produces. HyperLynx produces detailed reports that show which channels passed, which channels failed, and by how much. But by the time we have 336 channels in the report, it becomes difficult to see the forest for the trees. So for this demonstration, we're using a plotting utility that reads the HyperLynx report and produces a scatter plot for all the channels, showing eye height versus eye width. The protocol requirements are indicated by the red dashed lines, and the data points are shown in different colors, depending on categories. Here, the colors indicate the different interfaces in the system. This plot allows us to assess the performance of the entire system at a glance, making it easier for us to identify outliers, assess trends, and make comparative design decisions. This is our baseline performance of the system with 2D view models, which we'll come back to later. Now let's move on to running this analysis with 3D view models. When people simulate a routed net using 3D views, they typically model the net in 3 stages. First, they identify the areas of the net that require 3D models. Next, they cut those areas out of the board, create 3D projects, and solve them using a full-width solver. Finally, then assemble the net topology in a schematic editor by stitching the solved areas together with transmission lines, connector, and component package models. The methodology is called cut and stitch modeling, and doing it by hand is difficult, time-consuming, and error-prone. But that's what most people do. Using manual post-route extraction means that you won't be able to verify all the nets in your system because that will require too much effort. Typically, only a handful of nets get modeled and verified. The longest, the shortest, the nets that have the unusual routing, and a few random samples. This is what a typical post-route analysis might cover. Anything that doesn't get verified, well, that's just going back to our hope for the best strategy, isn't it? HyperLynx will let you verify all of the nets in your design automatically. You can reduce design risk by using HyperLynx to find those odd layout issues that theoretically shouldn't cause a problem, but often do. Anytime you can find and correct a layout problem before prototype fabrication, well, that's a lot of time and money saved. How does HyperLynx allow you to verify all of your serial links? By automating the entire extraction and analysis process front to back. You identify the nets of interest and the serial link protocol that you're using, and HyperLynx will do the rest. HyperLynx does all the topology extraction and modeling automatically, allowing you to trade off accuracy for turnaround time. 2D view modeling is lightning fast, and the 3D cut and stitch flow is fully automated. HyperLynx uses the DRC engine to find the areas on the board that require 3D modeling. The signal and its associated return path are fully modeled, and the area boundaries are chosen to ensure TEM flow at the signal ports. HyperLynx automatically creates the corresponding simulation projects for the 3D full-wave solver, ready to be solved in a batch analysis. In order for the cut and stitch methodology to be valid, the signal needs to be in TEM mode at the signal ports, and the majority of the signal's return path should be contained within the area, Here we see an animation of the via behavior for our design at the Nyquist frequency, showing both signal and return current. You can see the return current is well contained within the area, and therefore the methodology assumptions are valid. The 336 channels on our board will produce hundreds of critical areas that need to run in the full-wave solver. Running all of those jobs, one after the other, will take too long. HyperLynx lets us scale solver performance by running jobs in parallel. HyperLynx actually allows two forms of acceleration. We can add more cores to each job to make it run faster, and we can run jobs in parallel to make the total process run faster. HyperLynx job distribution supports a number of different distributed computing architectures so that you can configure the process based on what your resources have. HyperLynx job distribution makes it possible to front-end large simulation jobs with an ordinary laptop. Here, a laptop in Siemens, Massachusetts office is used to run solver jobs in the Oregon Siemens office. A total of 660 jobs were run, 30 at a time, using a total of 480 physical CPU cores. All the jobs were completed in 20.5 hours with 92% efficiency, meaning just 8% of the time was spent on computing and communication overhead, and that's with everything running remotely across the country. This means you can adjust solver performance to meet your turnaround needs. So how does our overall system behave? Here we see the results for all 336 channels colored by interface name. This allows us to see the behavior of the entire system at a glance. You'll notice the system is very well behaved with plenty of voltage and timing margin because we're analyzing a mature design in the typical corner. A design that's still in the layout typically wouldn't look this good. Here we see the same data, color-coded by signal direction. Notice the groupings here. Viewing different sets of plots side by side allows us to zero in on potential problem areas quickly. But how well did our 2D VIA simulations fare against their 3D counterparts? Here are the 2D results again, which took 3.5 hours to produce on a single laptop. And here are the 3D results, which we produced in just over 24 hours with the help of 8 high-performance servers. The results are decidedly different, but you can see the 2D results are surprisingly useful, especially since they can be produced so quickly and with relatively little compute power. Here's another good use for 2D VIA simulation, a quick stack-up study. This plot compares two different stack-ups to determine their relative effect on system margin. Once we had a baseline stack-up in zPlanner, it was easy to derive an alternative stack-up using lower-cost laminates. What's most interesting here is that the stack-up shown in blue costs about 45% less than the one shown in green. Before you conclude the low-cost stack-up is a slam dunk, remember, we're only looking at a typical case performance here. Still, you can see how this gives us a quick way to assess the relative impact of system-level trade-offs like stack-up design. Now, you might be dubious. Could this kind of post-route analysis really find the kind of needle in a haystack problem that might cause a board spin? So, as an example, we took one of the vias on one of the channels and corrupted up the backfill data. Normally, there is a short stub beneath the via, but we made the stub several layers deeper to emulate a case where the wrong value was entered inadvertently. As a reminder, here are normal results for the full system, and here are the results for the corrupted system. As you can see, the broken channel clearly stands out, such that we would track down and resolve this problem. And finally, let's take a quick look at IBIS-AMI simulation. IBIS-AMI models represent a specific vendor's actual silicon and are the most accurate way to predict serial link behavior. That said, they're also the most expertise and time-consuming analysis we can do. That's why it's important to take as many problems off the table as we can before we start running IBIS-AMI simulations. If we're finding basic problems with IBIS-AMI models, we're wasting our time. One added benefit by using the progressive verification methodology, by the time we get to IBIS-AMI simulation, the tough channel modeling work is already complete. And while we're talking about IBIS-AMI model simulation, please don't forget to see our joint paper with Ericsson on modeling DFE error propagation. This paper explores a new method for predicting DFE error signatures using statistical simulation methods. So, in conclusion, we discussed Siemens' progressive verification methodology that lets you run analysis in controlled stages to find and fix problems earlier. We showed how HyperLynx can automatically model and verify all the serial links in your design, and how you can scale simulation performance to meet your turnaround needs. And finally, we invite you to stop hoping for the best and start verifying your complete design with HyperLynx. Because, as we all know, it's easier with HyperLynx. Thank you for your time and attention. You can see more about HyperLynx at the demo stations over there, and more about stack-up design with Z Planner at the station on the other side of the wall behind me.